All right, I just finished the notes and the practice tests for the Unit 3. So this is my intro, but I'm making it after the fact. I'll just say that yeah, it's a longer study guide, and I don't, I took my time when explaining things. So obviously you don't have to watch the whole thing. You can just watch what you need to watch. If you need to watch the whole thing, watch the whole thing. If you don't need to, if you get these problems but don't get others, do the ones that you watch the parts you don't get, and take your time. And I'll see you in office hours. Have fun with the video. Okay, guys, welcome to the Unit 3 stat video, where I'll be walking through the tests as well as some of the notes from the unit. I've got the gaming headset on the gaming rig. This is going to be a high resolution video, high quality content. Make sure you like, subscribe, comment your initials down below for a giveaway. Make sure you know you've watched. I know you've watched the video. Okay, here we go. So we're gonna start with some notes. Just gonna go through from the beginning to the end. Like, what have we gone over this unit? Like, what are we doing here? So we're starting with definite integrals. This is where we start with the idea of Riemann sums, right? Which you're familiar with. Riemann sums. We got like the rectangles. We do like this. Essentially, the idea was, okay, let's make infinitely many of those rectangles and let's make them infinitely thin. And that's basically what happens here. This is where we got to. And instead of writing this big limit notation, we just write it as this symbol. So we have the integral from some start point to some end point of some function, which is called the integrand. And this itself, being able to convert from this to this, is on the AP test, is on the test, and we'll talk about that later. We'll get to a question about that. But basically, what is this giving you? This is giving you the area under the curve, the area between the curve and the x-axis of this function between these two bounds. That's what it is, and I'm sure you're all familiar with that by this point. And there are certain properties to definite integrals that you need to know. First one being the zero interval. Zero interval says that if you have an integral from some a to some a of some function f of x dx, this will equal 0. That's it, because essentially what you're saying is there's no width to your bounds. There's no width to it, so there's nothing there's no area there. Okay. The addition of intervals says that if you have an integral from a to b of f of x dx, and you add the integral from b to c of f of x dx, you'll get the integral of a to c f of x dx. And the way that I like to remember that is just like visually it makes sense, right? If you're from a to b, and you have this region, and then you add this region, then together you will have the total, which is a to c. Okay. Negation of interval. This is very very important. This one's also very, very important. This one says that if you have an integral written, quote, the wrong way around, meaning like the big numbers on the bottom and the small numbers on top, because a needs to be less than b, right? That's the way we write it. Then of some f of x dx. That can be rewritten as the integral from a to b, the negative integral of a to b f of x dx. Okay. Multiplication by a constant just says that if you have some integral a to b, k, some constant k of f of x dx, we can just take that k out. So it's k times the integral a to b f of x dx. Some difference says, let's center this. Some difference says if you have the same bounds, a to b f of x dx, plus the same bounds of another function, say g of x, then you can write it as one integral from a to b, and then inside of be f of x plus g of x dx. a big parenthesis on that. So this sum difference one is actually more important going the other way, going backwards. So actually, usually you have a situation written like this, and you want to make it simpler by separating it into like two separate intervals. So you usually go the other way on this one. Translation. The idea of this one is that if you have an interval from a to b of f(x) dx, that is equivalent to that same interval a plus some c of f of x minus c dx. What this one is saying is, oh, sorry, my bad, this should be a b, my bad. What this one is saying is that if you're moving your bounds of your integral some c to the right, and you move the function that same amount c to the right, then it's the same integral. So this is, just so you know, this moves function c to the right, and this here is moves the bounds c right. So if you're moving both of them together, then it never changed. That's the idea of this. Okay. Next we have indefinite intervals. Let me zoom out a little bit here. Indefinite intervals. Unlike definite intervals, and I may have jumped ahead here. 3.0. I'm missing antiderivative. My bad. Yes, antiderivatives. Definite intervals can be expressed as interval a to x, where a is a constant and x is a variable. This type of definite interval results in a function called the antiderivative, which is notated in an uppercase letter. So I think like a lot of the times people confuse like integrals and antiderivatives, or like confuse like what is the difference between them. And it's like they are very, very similar. You can see here this kind of integral is equal to the antiderivative, but that's not always true. And generally, like integral is a term that we use to refer to like the area under the curve, like we're talking about some shaded region. And antiderivative I think of as the specific function that is the antiderivative of another function. Antiderivative shown above can be interpreted as the area function, and will determine the area under the graph of y equals f of t from a to any value of x. Capital F of x can also be interpreted as an accumulation function, which computes the accumulated value of f from t equals a to any value of x. Okay. Antiderivative of a function is a function f whose derivative is little f, where the derivative of that capital F equals little f. And the antiderivative of this must be x squared plus 3x plus c. I'll put the c at the end, because the derivative of this is that. Okay. Since there's an infinite number of antiderivatives, there are only that are different only by a constant term called a family. We add the c, right? So the c represents all the constants, and this would be the general antiderivative. Okay. Next page, we're on indefinite intervals. Unlike definite intervals, which are defined by two bounds, indefinite intervals have no bounds. Are written in the form to be integral just f of x dx, no bounds. The indefinite interval represents all of the antiderivatives that are associated with every possible value for a. For that reason, an indefinite interval has infinitely many antiderivatives, each differing by a constant, right? So, example, integral x cubed would be x to the 4th over 4 plus c. Okay. Fundamental theorem of calculus. So this is what the unit's called. This is pretty important. The fundamental theorem of calculus says that if you have this antiderivative, this area function, from some constant a to x of f of t dt, then its derivative, the derivative of that, is equal to what you're integrating. The derivative of this is equal to this. That's this. Okay, for all x from a to b. Okay. So I mean, another way to write that is like d dx, which means to take the derivative of a dx f of t dt equals f of x. part 2. If capital F is any antiderivative of little f of x such that the derivative of capital F of x equals little f of x for all x in an open interval containing a to b, then we say that the integral a to b of f of x dx equals f of capital F of b minus capital F of a. Okay, continuing on. Inverse power rule. I mean, the most important rule in taking antiderivatives, for every x1 besides -1, and you will not see -1 on the test, we use the power rule to get our derivatives. We can do the inverse power rule to get our antiderivatives. So inverse power rule says if you take the integral of some x to the n, then that integral will equal x to the n plus 1 over n plus 1 plus c. Okay, that's the main rule. We've also got, I'll mention integral of sine x dx is, I should put the dx right here. The integral of sine, so you ask yourself, okay, what the derivative of what is sine? Well, the derivative of cosine is negative sine, so it must be the derivative of negative cosine x. That's going to get you sine x. And similar for integral of cosine x, well, the derivative of sine is cosine, so it must be sine x plus c. Okay. Those are the only antiderivative terms that you need to know, the only integrals you need to know. This is an example of the fundamental theorem of calculus, of how it's set up. So you have a definite integral, you take the antiderivative from a to b, and then you take the difference of the two. So also practice, I'll do this one. So first we're going to take the antiderivative of this, we're going to find capital F of x, so that's going to be, and also just be clear, guys. Make sure you're being very clear with your notation. I see some of you getting kind of lazy with what you're writing. Be really, really clear, like write what you're doing. So capital F of x here is going to be, okay, that's 2x squared over 2 plus 5x, which is going to simplify to x squared plus 5x from 4 to 9. 4 to 9. Okay. And we don't need to add the c because it's a definite integral, and it'll cancel out at the end. So then I'm going to do, okay, f of 9 minus f of 4, which is going to be 81 plus 45 minus 16 plus 20, which is, what is this, 126 minus 36, which is 90. So your answer here will be 90. Okay. Then move on to the applications. So this is like 3.1 through 3.4 is what I just went over, like the delta is 3.1 through 3.4. Now we're in 5 and 6, and like 5 and 6 are really the meat of the test, I'd say, and like they depend on you knowing 1 through 4 to understand what to do. And like a very, very key part of this unit and a part of calculus in general is this relationship between displacement, velocity, and acceleration. And I'm going to spend a lot of time in this video talking about this. So essentially you need to know, like, oftentimes in the test you'll be given one of these three things and you'll be asked for one of the others. So maybe you're given velocity and you're asked for acceleration, or you're given velocity and you want the change in position. And well, I think velocity to acceleration is really clear. So you're given velocity, you just take the derivative and you get acceleration. If you're given displacement or the position function, you just take the derivative and you get velocity. So that's easy. Going the other way, I think, is where it kind of starts to confuse people. Yes, velocity is the integral of acceleration. Yes, displacement is the integral of velocity. But there's all these other words that are used. So you've heard of the position function, you've heard of displacement, you've heard of distance. They're all kind of different, but the same at the same time. So I want to kind of clear that up here. This is on my other sheet. On the last sheet, I believe, right here. This one, yeah. So particle motion terms. But I actually think it makes sense to maybe mark it right here on the sheet where it's here. So yes, displacement is the integral of velocity, but like specifically, it's a definite integral of velocity from a to b, v of t dt. Like that is displacement, right? That is displacement. Versus the general indefinite integral of v of t is, and I'm forgetting the dt here, is s of t. So that's position. And these are different. So the general integral will give you that position. The definite integral will give you the change in position. So they're different. And then there's another one, which is distance traveled, the total distance traveled, and that's a to b of the absolute value of v of t. And that is total distance traveled. So I think this is where it kind of gets confusing. Is like, yeah, it's the integral of velocity that gives you displacement. Yes, and you can also get the general position function right here. And you can also get the total distance traveled, that's right here. So there's multiple different things that you can get. Similarly for acceleration, right? If I take the general integral of acceleration, the general integral of a of t dt, that will give me v of t. But if I took the definite integral, say a to b of a of t dt, this is going to give me the change in velocity. Similar to how displacement is the change in position, the definite integral of acceleration is giving me the change of velocity. So I think that'll start to make more sense, like the more we do the problems here, but that's the key. So acceleration, velocity, displacement. I will go over all this on the other side. So next is area between curves. This is gone. Like this is not on the test. Like I cut this. We're going to do this later in the year. Towards the end of the year, it's going to go with volume unit. So that's out. Last thing I want to go over is this. Oh yeah, this sheet here and the particle movement chart. So a key problem that comes up a lot in the test and this unit is this idea that you have a starting position, you have an ending position, and you're given a rate or you give velocity, and you want to know like where you end up. And I want to just review this because it's very, very important to know. And it's on your delta. This is 3.4, 3.5, 3.6. You got to know it. So I think method 2 I'm going to start with because it's the most intuitive. Method 2 works like this. You have a starting position, we'll call it S of P, SP. You take the integral from some starting time st to some ending time et of some rate. It doesn't have to be velocity. It can be any rate. So I'm going to just call it f prime of x dx, and that's going to give you your ending position. And I say ending position, I say starting position. That's usually like referring to velocity, but it could be like starting quantity and ending quantity. Like it could be any of those things. So let's use this as an example. So here, my starting position is 6. Look, it's at position x equals 6. So that's my position. It's my SP. So it's going to be 6. Plus, I'm given the time. Well, that's my starting time is 0, right? So it's going to be 0 down here. And I want the position at 3. So it's my ending time is 3. And then what's my rate? Well, my rate in this case is velocity. So velocity is negative 12t plus 9 dt. And this is going to give me my ending position. So here, the 6 is given to me. This I'm going to do fundamental theorem of calculus. So this is going to become negative 12t squared over 2 plus 9t from 0 to 3, which is just negative 6t squared. So we're going to plug in a 3. We're going to get negative 54 plus 27. And then when I plug in 0 for it, I'm just going to get 0, right? We get minus 0 plus 0. So my answer is negative 27. So what I do is, that 6 plus, this is negative 27. This whole expression is negative 27. That's going to get me negative 21. So this is method 2, and then I think it makes a lot of intuitive sense. Method 1 is, so let me go back to that other chart just to make sure this is clear. that. Here it is. So back to this. This is again like the confusion with displacement and position and stuff. So method 2 is using this. Like I'm taking the definite integral. I'm taking that. I'm getting that displacement. I'm getting the change in the rate, right? The change in the rate. That's what I'm doing. Versus method 1 is getting this. Is doing this method. So that's what I'm going to do. So I'll mark that here. So method 2 is using this idea that the integral from a to b of some rate is going to give me the displacement or like change in quantity between two times. Versus position function, we go straight for the antiderivative. So we're going to take the integral of negative 12t plus 9, and we already did this. You get dt. You're going to get negative 6t squared plus 9t, but plus c, because this is an indefinite interval, we need to add that plus c. So here's the issue. I have position here. This is the position function s of t, but I don't know the c. So I can plug in a 3, right? I want to know where it is 3, but like I'm going to be ending with a c at the end, so I'm not going to know really where it is. So we have to solve for c. To solve for c, I use what is given to me, this known position. So I know that it's at 6 when t is 0. So what you do is you say, okay, well, it's going to be 6 when t is 0. So we're going to put a 6 over here and put 0 for all the t's. So we have negative 6 times 0 squared plus 9 times 0 plus the c. So that means 6 must equal c. Okay. Okay. And so since we know that 6 equals c, I can then replace that into this function here. So I can write it as s of t equals negative 6t squared plus 9t plus 6. And now I have my real position function without the c, and I apply 3. So I'm going to do s of 3. That's going to get me negative 6 times 3 squared plus 9 times 3 plus 6. And if you evaluate that, you'll get that equals negative 21. And notice that that is the exact same answer. So this is the method 1. This is where you integrate, solve for the c, plug the c back in, and then plug in the time. Versus method 2, you have the starting point, and you get the definite integral of the rate to get your endpoint. Both are important, both you need to know. I think this one gets a little more use, especially in the calculator portion, because you have to use this method. Down here, again, rate in, rate out, that got cut, that's out. Did not get to cover that. You'll have to wait until next unit. Sorry, guys. Then we have displacement. So displacement, again, I'm just going to say it again because it is very important. It's the integral of v of t dt, which is change in position. You know, it can also be talked about as a quantity, changing quantity. Distance is same thing, integral a to v of the absolute value v of t dt, and this is going to give you like total distance traveled. Okay, and speed is just the absolute value of velocity. Okay. So on the back here we had the curve analysis charts. Curve analysis charts are the same. They're both the same thing, top and bottom. I will, rather than doing this one, I'm going to do the last one, which is, let's see here, right here. And this is because this is the same chart. So it's the same chart 3 times, and I'm only going to do it once because I don't need to repeat myself. Particle movement chart. So the particle movement chart is the overlap between the curve analysis charts and the physics, the applications of physics that come from calculus. So the idea of it is, okay, well, the function is essentially the position. the first derivative is essentially velocity, and the second derivative is acceleration. The way this works is like, and you can see the relationship. This is position, the first derivative of position is velocity, and the second derivative of position is the acceleration. And we talk about units, and when, as far as position goes, this will always be a length. This will always be a length over some time, and this will always be some length over some time squared. It's not exclusive to these three either. I mean, this is for specifically for position, but if we talk about other derivatives, it could be anything. It could be any rates, but the key thing is that the denominator of that rate keeps getting, you know, multiplied by itself as you go along, and that's the same. So the structure of this stays the same, but these words top and bottom can change depending on the context. If you're doing money per coffee, you know, money per coffee, it would be like, you know, I'll do it. It would be like money for the first derivative, or for the quantity, and it would be money for coffee for this for the rate, and then for the second rate, or the rate of the rate, it will be money per coffee squared, right? So it doesn't matter what the words are, it always follows that structure. Just want to make sure that's clear. But specifically back to particle motion, talking about particle motion, when it's increasing, it's moving right, or it's moving up, or up. Decreasing is moving down or left. Relative maximums and relative minimums, both of these are called turning points. Okay, which is like changing direction. So like this could be right to left or up to down, and this would be the other way around. So this is okay, right to left or up to down, and this is opposite, left to right, down to up. They're both called turning points. Critical points are just anywhere where it equals 0. I just want to make sure, like, when the derivative equals 0, if v, I'll put that over here, if the velocity equals 0, then particle is at rest. Right here you say particle at rest. Okay. Or sometimes it can be v of t, it's just undefined. Okay. But the connection here is important, that when the velocity is 0, the particle is at rest. Inflection point, concavity, speeding up, slowing down. Okay, so concave up means positive acceleration. Concave down means negative acceleration. Speeding up, we'll talk about that in a second. Inflection point would be changing acceleration. Right, we're going from positive to negative acceleration, or vice versa. I mean, speeding up and slowing down are exactly what they sound like. Now we'll talk about like when this happens. So we move right or up when velocity is positive. It's that easy. When v of t is above 0, and again, you can think of this like the first derivative when that's above 0. You can kind of think of them like the same thing. We don't worry about the second derivative here. Decreasing is when velocity is negative, or like the first derivative is negative. Nothing there. Relative maximums, so both of these happen when the velocity equals 0, and then this one would be going from positive to negative, and this one would be going from negative to positive. So again, the velocity equals 0. Sorry, this is really confusing. That should not be a, oh my goodness, that should not be a prime there. Just v of t equals 0. Okay. I covered critical points. It's when it's 0 or undefined. And then we have, let's talk about second derivative here. So yeah, right now you don't need to be concerned. There is something here, but we're not going to concern ourselves with it right now for relative min and relative max. We'll do that next unit. Then we're at inflection, concave up, concave down. So this just means if you have positive acceleration, then your velocity is increasing. So you say v dt increasing. It makes sense, right? Like increasing speed. That's positive acceleration, increasing speed, right? Versus if it's negative acceleration, v of t is decreasing. So you're like reversing, right? You're getting faster reversing. And if that's true, then a of t must be positive, and here a of t must be negative. And then above here, inflection points, a of t is going to equal 0, and change signs. And then for the inflection here, it's going to be an extrema. Right? You're going to have an extrema in velocity. When you're speeding up, v of t and a of t have same sign. So for example, both positive, both negative. Slowing down, v of t and a of t have opposite signs. Okay, that's it for the notes. Moving on to the test. Okay, so we're finally on the test now. So just a reminder, I mean, you already know all this, but test is the 17th. Part of it will be graphing calculator, part of it will not have a graphing calculator. And make sure you get your delta in by the 17th. Really can't emphasize that enough, guys. Like the delta, so key, so important. You know what to do here. I'll have lots of office hours this week, as well as on Friday, as always. I mean, this is, I've already gone over the notes. I just did that in the earlier part. Now let's go to the questions. Okay, first one here. So these are all calculators. This is really important. These are all graphing calculator, and the calculator skills are really important for the test. And a lot of what you learn this unit, I would say, is like just generally how to use the graphing calculator. And as we go through this, I'm going to use the good old-fashioned TI-83 because I want to show you that it doesn't really matter, guys, what kind of calculator you have. They all do the same thing, and they all get you from A to B. So it doesn't really matter. It doesn't matter having the fancy one or not. It's nice, but you don't need it. So let's look at this one. We have this function. G of x is the integral from 0 to x sine t squared d of t, and you want to know where it's decreasing. Okay, so this is using the fundamental theorem of calculus and using that and curve analysis. You know it's decreasing when its derivative is negative, right? When the derivative of g is negative, it is decreasing. These are the same thing. Okay, so I just need to find out where that's negative. Well, what is the derivative of g of x? Well, this is fundamental theorem of calculus part 1. The derivative of g of x is just the integrand here. It's sine x squared. So what I'm going to do is I'm going to graph sine x squared. It's going to go for y1. So here you're going to go to your calculator. You're going to go to y1. Let me clear all this out. Sorry. Is that better? No, that's not any better. Let's keep that up. Little fun fact here, you can actually up the brightness of your calculator by clicking second and then the up key. This is hopefully going to up the brightness a little bit. Okay. And I'll try and make sure there's no glare on it. Anyway, so sine x squared, easy. And we're going to change the window. This is very important. See how it says from -1 to 3? So we need to make sure our window says like -1 to 3. And then the scale should be 1. I don't know why mine says that. Graph it. Go ahead and graph it. And we're looking for where it's negative. Okay, so see here, we can see that it's negative here. So I need to find out, okay, where is this exactly? Now, I can find it exactly by clicking second. Let me show you what I'm doing. Second right here, and then trace gets you to this screen. And you're going to go for 0. You're going to move your cursor to the left, to the right rather. You're going to mark 1 point to the left of that the 0, so the left of the intersection, and 1 point below it, and 1 point in the middle, and that's going to give you. So it's 1.772. So already I know which one it is. I know the answer, guys, but I'll still show you it. So one of my points is 1.772, and I'll show you the other one. Good for practice because you need to know how to do this. We're going to go back and go to intersect, and then I'll go for the right. Sorry, not intersect, my bad. It is 0. My mistake. 0. Same thing off to the left. We have the left bound, so point on the left side of the intersection, a point on the right side of the intersection, and then a point in the middle. And that intersection is 2.507. So my other one is x equals 2.507. So it's negative between these two, therefore it must be decreasing between these two, therefore it must be D. Okay, I mean, I could have gotten that faster, right? Because as soon as I saw the 1.772, I knew it was that one, but I just want to show you. Next one, water is pumped out of the lake at a rate, R of t equals 12 root t over t plus 1 cubic meters per minute, where t is measured in minutes. How much water is pumped from the time 0 to 5? So again, like, this is really, really key, that the integral, I keep saying this, the integral of a rate, some, you know, f prime of x, the x, between a and some b, will give me the quantity, the change in quantity. Change in quantity from A to B. So if I want the change in quantity, right, that's how much water is pumped in the lake. Like, I want to know the different, like, how much more water was pumped. That's what this is. Like, it's the change in the amount of water pumped. That's going to get me that. So I'm going to take the integral. Take the integral of from 0 to 5 of 12 root t over t plus 1 dt. This is your answer. Like, this is it. You just have to do this on the calculator. So I guess, like, a key thing here, if you're asked about a quantity, how much water, and you're given a rate, right, you're going to take the integral of that rate to get the quantity. Take the integral of it, right? Say that. I mean, take the integral of rate to get the quantity. I think that that's such an important thing to know. Like, integral of rate will get me a quantity, right? That's key. So here we go. Calculator time. To do a definite integral, you should know this. Math 9, and we are integrating. First, you're at the function, so it's 12 root x over x plus 1. Now, careful here. When I'm typing the calculator, in the numerator and denominator, it's really good habit to put them in parentheses in the fraction. So it's going to be parentheses x plus 1. You want to make sure that's in parentheses. If it's not, you're not going to get the right answer. Comma x, comma my lower bound 0, comma my upper bound 5. Close it out. Okay, I made a mistake. This is a learning opportunity. So what did I mess up on here? 12 root x divided by x plus 1. Oh, I see the issue. I did not close out that parentheses. So this is a good learning opportunity because I made a mistake. Since I forgot a parentheses, that's the problem right now. So a key thing, guys, when you're in the calculator is that every parentheses should have a pairing parenthesis, if that makes sense. So see how, like, let me use my pen here. See how this parenthesis right here matches with this one right here? And this one right here matches with that one right there. But this one does not match with anything. It has no pair. That's my problem right now. So I need to insert that other square root right here, like right after this. So to do that, I go here, click second, then delete, that lets me insert. So right here I'm going to insert a parentheses. Now I'll be good to go. Click enter. Also, this is a very slow calculator, so it takes a minute to come up. We're waiting. Let's see. 47.193. So, and lucky enough, I see that answer here. It's a D. Okay, next one. This is an initial value problem, right? So I'm told that I did this in notes. I'm assuming a lot of you didn't watch that notes part, so I'm just going to write it again. That you have the starting position plus the integral of starting time to ending time of the rate f prime of x will get you my ending position. And again, the position is irrelevant. The position can be quantity, it can be starting quantity, ending quantity. It can be a lot of different things, but this is like the skeleton you work with. You know, this is the template, and you're just plugging in the values. So starting position is this value here. That's my SP right here. So I'm going to do 1 plus, and then 0 and the 2 are my two times. I call them times, but They're just inputs. The time helps me make sense of it. And then my derivative is, or my rate is sine pi e to the x all over 2 dx. Again, in the calculator. So it's a lot of math 9. Math 9. Now we're going to put in the function sine parentheses. Now remember how I said, like, in the numerator, just put it all as one big parentheses. So that's what I'm doing. So I'm adding another parentheses here. So pi, that's second, then the up sign. I'll show you what I'm doing there. That's right here. Pi, then e to the is right here, the ln right here. So second ln, e to the x, close that, close the next one, divided by 2, comma x, comma 0, comma 2. So that's my function up top, sine, that's my numerator, pi e to the x, then divided by my denominator 2. I don't need parentheses in that denominator because it's just one number. It's when it's like more than one thing, that's when you have to add the parentheses for the fraction. Oh my goodness. Alright, I'm making so many lovely mistakes here. What did I do wrong? So again, it's usually that the parentheses are not matching. Let's see. That parentheses matches that one. This sign, yeah, I have too much here, don't I? Yes, I'm missing a parentheses right here again. So I'm going to do a second insert. I'm going to close that. Yep, that would be the problem. Alright. Clicking enter, waiting. It's good learning. It's good learning, guys. So, okay, it's 0.157. This is 0.157. Plus that 1 is 1.157. So it must be E. Okay. 4. This is the same problem. I think I gave you 2 of these just to make sure that you knew how to do them. I'm going to do this one faster. Starting position 0.4 plus the integral from 2 to 5 of that derivative 1 plus 2x to the third dx. Let's do it. So math 9. The function is the square root of 1 plus 2x to the third. Little hint here. You can do to the power of 3, but you can also do this math 3 is to the third power. Little trick there. Then comma x comma 2 comma 5. Close it. Enter. 28.605. This is 28.605. Do not forget to add that initial value. You can see right here, they're trying to trick you. Look, 28.605 is one of the answers. So we, oh my god, I got the right answer. No, you didn't. You didn't add the plus 0.4. So you gotta add plus 0.4. And you get 29.05, which is A. Alright. This is gonna be a long video. Okay, 5. Particle moves along the axis. Position is x equals 1, t equals 2, and then what is it at t equals 4. So again, it's this. These are all the same. Yeah, and I gave you 3 of them because I was like, oh yeah, you really need to know these because they are important. So start at 1 plus integral 2, starting, ending, 4, 2 to 4 of 4 over t cubed plus 1 dt. So this like forces you to practice writing in the calculator, which is the test. Like you need to know how to do this. Like it's the test. Math 9. My function is 4. So again, no parentheses on the 4 because I don't need to because it's by itself. But on the bottom, the t cubed plus 1, I need parentheses for that. So I'm going to start new parentheses, x, and then math 3 is cubed plus 1. And I'm going to close that parentheses. And then I'm going to do comma, x, comma, 2 comma 4. Close it. Close it. 0.352 plus the 1. 1.353, which is C. Okay. There we go. 6. A particle travels along a straight line 3e to the negative t over 2 sine 2t meters per second. What is the total distance traveled in meters traveled by the particle? So keyword here is total distance traveled. That's key, because that indicates we're doing something different. Total distance traveled is different. So to get total distance traveled, I did this in the notes, but it's integral a to b absolute value of v of t dt. So let's do that. We're going to do integral from 0 to 2 times the absolute value of 3e to the negative t over 2 sine 2t dt, and then close the absolute value. So if you just wrote this on your paper, like, I would absolutely give you the majority of the points. I would give you, if this is worth 4 points, I would give you 3 points just for writing this, because this tells me you know exactly what to do here. And this, you know what to do. So you must, if you didn't get this right from this point, you just didn't write it in the calculator correctly, right? So I'm going to give you most of the points if you write this. But let's practice writing in the calculator, because that's important. Math 9. The function 3 second ln e to the negative x divided by 2, close it, sine 2x, close it, comma, x, comma, 0, comma, 2, close it, and enter. Oh my goodness, okay, I made a mistake here. I am filled with mistakes on this Friday night. This is not correct yet. Do not write this down. But I'm showing you this is a good example because I forgot a very important step. And that is, you found, right now I have displacement. And you can see this is an answer right here. This is an answer. So this is clearly trying to trick you here, but this is not correct. What did I forget? I forgot to take the absolute value because it's the absolute value velocity. So you need to go back up. So second enter will give me that previous entry. Then I'm going to go back, and then right before that 3, I'm going to go second insert, and then I'm going to go math num abs. This is going to give me the absolute value, and then I just got to make sure to close that off at the end of where I want it to be closed right here. And now I've got it. All right, I am sorry about the mistakes, guys. Like, I am sick. That's all I can say. I'm sick, and I'm sorry. All right. But I'm getting the right answer, and it's good learning because you're seeing mistakes and you're seeing how I fix those mistakes, and I recognize why they're wrong. Okay. Here we go. Taking its time, taking its sweet time. 2.261. So that's going to be this one right here. D. All right. For t greater than or equal to 0, the velocity of a particle moving along the x-axis is given by v of t equals cosine 8e to the negative 0.2 over negative 0.2t. The initial, the initial position of the function is 2.5. What's the displacement of the particle from time t equals 0 to t equals 15? So this is interesting. It's not asking for the final position. So this is kind of a red herring, this right here, because you don't need this. It's just asking for displacement. And displacement is similar to this, but not the not with the absolute value. It's just a of b, v of t, dt. So I don't need to do the absolute value. So we're going to say here, integral from 0 to 15 of cosine 8e negative 0.2 t dt. Again, writing it gets you points. Write it down. Write what you're doing down. I want you to write it down. Here, let's do it. Math 9 cosine 8 e to the power of second ln e to the power of negative 0.2x. Close it again for the cosine, comma x, comma 0, comma 15. Close it. Hopefully that's right. There it is. And this will give me the displacement. You guys should be getting really good at writing things in your calculator. 2.526. There we go. Write it out. Write it out. Write it out. All right. A music group expects to sell a new compact disc CD at the rate of R of t equals 20,000 e to the negative 0.12 t CDs per week, where t denotes the number of weeks since the CDs was first released. To the nearest thousandth, how many CDs are expected to be sold during the first 12 weeks after release? Okay. So this is similar to the first problem actually, where it's like giving you a context, and it's not velocity, it's not position, it's just asking for like a quantity. And like, again, when you see like how many CDs, you're like, okay, and I'm given a rate, I want to take an integral of that rate. So let's take the integral. Integral, it says first 12 weeks, so that would be from 0 to 12. And then this would be the disk sold. 20,000 e to the negative 0.12 t dt. And you might be like, okay, well, why is it not absolute valued? Well, I don't need to really worry about absolute valuing this because of the context of the question. First of all, only absolute value when it says total distance. That's the rule. Like when you see total distance, absolute value it. In this case, if you want a quantity, the way this is written is that it's already always positive here anyway. So it doesn't matter. In the context of the question, you can just take the regular integral. Math 9, here we go. 20,000, 20, 1, 2, 3, e to the second ln, e to the negative 0.12x, close it, comma, x, comma, 0, comma, 12, enter. About 127,000. So the closest one is 127,000. That's going to be the one. So it's about to the nearest thousandth, right? So I don't need to worry about more specific. Okay, 3 more left in the calculator portion. Multiple choice. The velocity of a particle moving along straight time is given by v of t equals 1.3 t ln 0.2 t plus 0.4. What is the acceleration? All right, this is a nice one. This is a gimme on the test. This is a gimme because you will know this little chart here, and you know which direction to go in based on what you're given. So right now, I was given velocity and I need acceleration, so I just need to know. You know, take the derivative. Acceleration is the rate of change of velocity. How is the velocity changing? That's the acceleration. So let's do it. This one is math 8, not math 9, math 8. And then we're going to do, I mean, you could say, if you want to show your work for this one, this is what you'd say. V prime of t equals a of t. And then you say v prime of 1.2 equals, write that down. Again, points, 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 points. Even if you did it wrong on the calculator, still your points. 1.3x ln 0.2x, you said okay, ln 0.2x plus 0.4, close it, comma, x, comma, 1.2, enter. Negative 0.093, which I see right there. Particle moves on the x-axis with velocity v of t equals 3t to the 4th minus 11t squared plus 9t minus 2 for negative 3 to 3. How many times does the particle change direction as t increases from negative 2 to 3? I need to graph it. So this is back. This is that the chart. Let me bring that up briefly. So you know this chart, and so changing directions are these points, right? The turning points. This is changing direction. So you know that happens basically when the velocity equals 0 and changes signs. That's where it's changing direction. So how many times does it change direction is all it's saying. So we're going to go here. We're going to plot it. So we have 3x to the 4th plus 9x minus 2. Window, which you make your window right. So it's going to be negative 3 to 3. Let's have a look at it. And how many times does it cross over? So 1, 2. That's it. Just 2. The answer is just 2. Okay, last one here. A particle moves along. Oh, just to be clear here, back on this for a second. This would be changing, increasing to decreasing, or right to left. And this is going from down to up, or left to right. So just remember that bottom here is left or down, top here is up or right. Okay. A particle moves along a line. I have the velocity negative t cubed plus t 2t squared plus 2 to the negative t. So that's really hard to see there. For what values of t is the speed of the particle increasing? So we need to graph it. first. I'm going to graph it first. So it's going to be negative x, and then math 3 to get cubed, plus 2x squared plus 2 to the power of negative x. And it doesn't give me a window, so I don't think about it too much. I do see some signs over here, like where I'm roughly supposed to be at, somewhere between 0 and 3 for most of them. So looking at this, I can tell what's going on. Oh, it is t is greater than or equal to 0, so I could make, I'll go ahead and do that. My x min should be 0 because it doesn't go below that. So I'm looking at this, I'm looking at velocity, and I'm asked, where is it increasing in speed? So you can do this without doing any more than that. I'm going to show you like the intuitive way, and then I'll show you like the analytical way. So if you look at this, right, this is velocity. And so velocity right here, what's it doing? It's positive, right? And it's getting more positive. So this zone right here is increasing in speed. And if I like wanted to see roughly, okay, what roughly is that? Well, it looks like it's around like 1.24. It like starts doing that, and then, or see, it ends doing that. And then over here, kind of about around the beginning, 0.09 or something. It's like it starts doing that. Okay, so from then to then, it looks like it's increasing in speed up until 1.25-ish, and then see it's decreasing in speed here because like the velocity is coming down, velocity is approaching 0. As velocity approaches 0, it's decreasing in speed, it's slowing down. But as soon as it hits this point, it starts to increase in speed again. It's getting more negative in speed. So this right here, this is increasing in speed, and this is increasing in speed. So just by looking at the graph, I can tell you the answer is E. I can do that just by looking at the graph, but I'm going to tell you like more specifically, a more specific way of knowing how to do it. And that's just by like moving my cursor and sort of just seeing. But you can also do that. So you can do y equals, and I'm going to take the derivative of that. So I'm going to find acceleration. So it's speeding up specifically when velocity v of t and a of t same sign. When they're the same sign, it's speeding up. So let's do that. Here, math 8. I'll show you a trick here. So rather than retyping all of y1 back in, I'm going to do vars, yvars, function y1, comma, x, comma, x. This is going to graph the derivative. So right here, you're now looking at the derivative. So you're looking at velocity and acceleration. This is velocity, what we've already drawn right here. And what's being sketched right now is acceleration. This is the acceleration of the particle. So what you can see from this is, which is what I said, that they're both positive on this interval here, and then they're both negative on this interval here. From this point to the right, see they're both negative here? I mean, you can't see it, but this one's going down here. It's definitely negative. And then right here in this interval, they're both positive. And if I really wanted to know what were those values, I could do a 0 of this one, and I'd go to left here, and I'd go to the right here, and then I'd go in between, and you'd see that it takes absolutely ages, but it's 1.256, and look, that's 1.256 here. Like I can see by looking at those zeros here what the coordinates would be. Okay, so that is the multiple choice of the practice test. Okay, continuing on with the MCQ. This is now no graphic. In fact, this is no calculator at all. I'm not going to use any kind of calculator here. You don't need any calculator to do these problems. So first one, we're looking at a differential function, and h is the area function from 0 to x of f of t dt, and which correctly orders these. So you were actually familiar with these probably from the last test, but it wasn't an area function. It would have just been this, right? And it would have been like f, and this would have been like f prime and f double prime. The difference here is the function is the area function, not the function itself. So this is fundamental theorem of calculus, saying that the derivative of h of x would be f of x, and then the second derivative of h of x is the first derivative of f of x. And remember, this is f of x, so you're looking at it. Okay, So if we think about the h of 2, what does h of 2 look like? Well, it's just the area from 0 to 2. So it's this region right here. And it's clear that h of 2 is a positive number. You know, I don't need to know what it is. I just need to know that it's positive. That's a plus right here. Okay. And then h prime of 2 is a derivative of h at 2. Well, that's f of 2. This just means f of 2. So you go to f of 2 is 0. So h prime of 2 is 0. This is some positive number. And then we've got the double prime, which is going to be f prime of 2, which is the slope at 2. And you see the slope here. The slope is, look, going down, it's negative. So it's going to be some negative value. I don't need to know what it is, just know if it's positive, 0, negative. That's how these questions work. So then I'm just going to order them. H of 2 is going to be the biggest, so let's looking at this one, and then here. So again, this is positive, 0, negative, so it's got to be E. Okay. 2. We have a piecewise linear function given by h of x is -1x, on which of the following is h increasing. So this is very similar to actually the calculator question. You know it's increasing when its derivative is positive, which is again is the derivative here, h prime of x is f of x. So I'm looking for where f of x is a positive or above 0. And so we look here, so where's above 0 as well? From 3 to 9. So that's it, 3 to 9. Easy. Okay. 3. If the antiderivative is equal to the 0 to x, integral from 0 to x of t cubed plus 1, then the derivative of f at 2 is, so what this is saying is, we're going to take the derivative of this, and then we're going to plug in a 2. Okay, so well, what is the derivative of capital F of x here? Well, the derivative, again, this is coming out of thermal calculus, it's just this. This is the derivative of the whole area function. So we would say that's just root x cubed plus 1. And then I'm just going to plug a 2 into that. So plug a 2 into that, I'm going to get 2 to the third is 8 plus 1. That's root 9, which is 3. Okay, so the answer is D, 3. A particle moves along the x-axis with velocity 3t squared minus 4. The particle is in position -2 at time 0. What is the position of the particle at time t equals 3? So this is very similar to the calculator problems. There's two ways to do it. I guess I'll do both ways. So we have method 1. This is from the notes, method 1. Method 1. You're going to take the integral of e of t, which is 3t squared minus 4. It's going to get you t cubed minus 4t plus c. This is s of t right here. And then you got to solve for c. To solve for c, we're going to plug in a -2 and a 0. So we're going to say -2 when t is 0, so 0 to the third minus 4 times 0 plus c. So c just equals -2. So really my position function is s of t equals t cubed minus 4t minus 2. Then I'm going to plug in the 3. So it's going to be s of 3 equals 3 cubed minus 4 times 3 minus 2. That's 27 minus 12. That's 15 minus 13. S of 3 equals 13. And I went into more, if you want more detail about method 1, that's in the notes part of this video at the beginning. Method 2 is the starting point, endpoint 1. That's what we were doing in the previous problems. Way back here. It's the same as here. It's the same as this. It's the same format as this. Starting point, starting time, ending time, and then the ending point. That's what I'm doing here. The only difference is I can't use Math 9. I gotta use, I have to do it by hand. So I have to use Fundamental Theory of Calculus Part 2. So it's gonna be, my starting point is -2. It's gonna be -2 plus the integral from 0 to 3. of 3t squared minus 4 dt. Now we're going to take the antiderivative, and just like this, the same as this over here, it's going to be t cubed minus 4t from 0 to 3. I'm going to plug in a 3, so we get 3 cubed minus 4 times 3 minus, and then it's just to be 0 cubed minus 4 times 0. That just makes it 0, so I don't have to worry. It's 27 minus 12 is 15. So this whole thing, this whole expression right here just equals 15, and then I have negative 2 plus 15 is 13. So you can see both methods get me to 13. Method 2, method 1. Next one. The graph of the function is g of x is integral from 1x of t dt. What values of x in the interval 0.5 to 6.5 does it have a relative maximum? So relative maximum is going to be, so I'm going to review this. Relative maximums happen when the derivative of the function changes, equals 0, and changes from positive to negative. Right? That's from the table. Specifically, the derivative of g of x is f of x. And again, this is f of x here. So you're just looking at where this hits 0 and goes from positive to negative. And that's going to happen at 1. Because here it's hitting 0 and it's going from positive to negative. So that's going to be a relative max. And then this one would be a relative min. But it's not a solution because it's not a relative max. And then this one is neither. Okay, so here it's 1 only. Okay. This is number 6. Let f be given by a function f of x equals the integral from x of negative t squared plus 2t plus 3. On what intervals is f increasing? So you should know by now that f is increasing whenever its derivative, f prime of x, is positive. So you know, this is fundamental theorem of calculus. The derivative of f of x is just this. This is f prime of x right here. So say that f prime of x equals negative t squared plus 2t plus 3. And we need to find out where this is positive. And in order to do that, we're going to set it equal to 0, and we're going to factor it. Before you start factoring, it's really always a good habit. You always want to make sure that your squared value is positive. Right? I don't like this the way it's written. I want to make that squared value positive. So I'm going to take out a negative 1 out of everything here. So put a negative 1 out front. It's going to divide every term by negative 1. It's going to turn that into a t squared, a minus 2t, and a minus 3. Now it's a lot nicer. Now I can factor this. Negative 1. Two numbers that multiply get negative 3, add to get negative 2 are t minus 3, t plus 1. And I could have made this x, by the way. You could have done this with just x. I don't know why I kept it as t. So my solutions are t equals 3 and t equals negative 1. Which makes sense because you see like these negative ones. Like, you know you're on the right track when like this should match this, right? So like if I got like 7 and 1, right, I'm like something's kind of wrong here. The other thing is like 0 is not a solution here. I saw some people do this in the last test. Like the 0 is not a solution for this. Like it has to have an x to be for 0 to be a solution. If it was like negative x or negative x squared, that would be 0. But no x, no solution. You draw this out. We're going to have negative 1. We're going to have 3. Then we're going to plug it in here. So 3 plus, so plug in like a 5. You can get positive, positive, negative, negative. Plug in a 2. You're going to get positive, negative, negative, positive. Plug in a negative 1, sorry, negative 2. You're going to get negative, 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 right? If you have an odd number of negatives, it's going to be negative. If you have an even number of negatives, it's going to be positive. That's basically the rule. So there we go. Negative 1 to 3 has to be. Okay. Okay. Continuing on, we have some integral properties. Yeah, these are really important ones, and you can definitely expect to see some of these So definitely be used to like how to deal with the integrals. So here we have 4 to negative 10 is negative 3, and 4 to 6 is 5, and I want negative 10 to 6. So the thing I always like to do first, I like to convert them. So every time that I see like it's in the wrong order, so B to A right here instead of A to B, I'm going to rewrite it. So I'm going to say integral negative 10 to 4 g of x dx is positive 3. This is a lot nicer now. Now I have them all in the right order. I'm going to draw my line, put negative 10, 4, 6. I know that negative 10 to 4 is 3. I know that 4 to 6 is 5. So altogether, this must be 8. So it's 8, because 3 plus 5 is 8. Once you convert them and you draw it out, it's not so bad. Similar here. So a little more complicated. This is again something you can expect. I want 0 to 3. And I want f of x and the f of x and g of x together in here. So I'm going to have to get 0 to 3 of each of those separately over here. So let's start with g of x. G of x looks kind of easy, just in the wrong way around. So integral 0 to 3 of g of x is dx is just 7. Okay, so here I'm also going to help you by kind of rewriting this. I'm going to write this as 1/2 integral 0 to 3 f of x dx plus, my bad, minus, the minus there, integral 3 times the integral of g of x dx. And I know, oh my god, 0 to 3. So I know that the integral of 0 to 3 g of x dx is 7. So this is 3 times 7. So this is really just saying minus 21. Is that clear? Like, that's 7. So I'm just like plugging it in here and then times it by 3. We get 21. It's minus 21. And I got that by just splitting this up, and that's using the integral property rules. Here, I need f of x. So I have 0 to 6, and I have 3 to 6. So I can get 0 to 3 by, I'll do a little chart of this, what this looks like. You're doing like, I know 0 to 6 is 9, and I know 3 to 6 is 5. So 9 minus 5, this must be 4. So 0 to 3 must be 4. So I can say integral 0 to 3 f of x dx must equal 4. So right here, this is really saying 4 divided by 2, that's 2. Right, so it's 1/2 times 4. Right, this is really, should I label that here? This is really a 4 right here. And this is really a 7 here. Right, so that's 2 minus 21, that's negative 19. So that's my answer, B. I think just like take your time with these, draw the number lines out, make sure that they're in the right order from low to high, make sure to convert them. Take your time, separate. If you see like a big complicated integral, like separate it out, relax. That's my advice. Where is it concave down? Okay, so we have a function, f of x is 0 to x, 2t cubed minus 15 squared plus 36t, on which the intervals is a concave down. Okay, so concave down, again, you gotta know it. That's when the second derivative is negative. So what is the second derivative? Well, the first derivative, recall, is just what's inside here. That's the first derivative of f of x. That's just 2x to the third minus 15x squared plus 36x. So then the second derivative is just the derivative of that. Power rule, 6x squared minus 30x plus 36. And now we do the same thing we did up here. We're going to set that equals 0. So we're going to factor out the greatest common factor, which is 6. 6 comes out, x squared minus 5x plus 6. 6 stays. Two numbers that multiply get 6, add to get negative 5. That's x minus 2, x minus 3. So solutions are x equals 2 and x equals 3. That's it. So now number line 2, 3. That's test points. So it's test of 4. Positive, 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 positive. Test 2.5. So it's going to be negative, positive, positive, negative. And we'll test like a 0, negative, negative, positive, positive. Okay. So where is it concave down? Just this interval here, 2 to 3. So again, you know, there's some tactics with multiple choice and like whether or not you're on the right track or not. If you're like not seeing, if you got like weird numbers here, you're like not even seeing them as an option, you know you messed up. Like you got to go back, like refactor it, just look at it differently. Next one. P says linear function. What is the value of integral -1 to 9, 3 f of x plus 2? I'm going to do the same thing I did in the other one, where I'm going to like just separate this into two things. So I'm going to write this as 3 integral -1 9 f of x dx plus integral -1 to 9 2 dx. And I think by splitting it up, it makes things seem a lot easier, and like things seem a lot like more palatable to get. So first thing here, I just need to get the area from -1 to 9 right here. So let's do that. I need the area from here to here. So right here, this is 1, 2, 3. So this is -3.5 because of this is a half. I can even see it visually. It's a half, right? Then here I have just a big triangle. So it's going to be a height of 2. It's 2 by 1, 2, 3, 4, 5, 6. So 2 times 6, 12 divided by 2 is 6. So the total here is 6 minus 3.5 is 2.5. So this is 3 times 2.5. That's it. So that 2.5 equals the integral -1 to 9 of f of x dx, which is 2.5, which is 7.5. Yep. So don't be fooled, because 7.5 is an option, but we didn't do this second part. Oh, and this is also another trick. You might be tempted to say, oh, it must be 9.5 because I just added 2. Well, you're not just adding a 2. You're adding an integral of 2, an integral of from -1 to 9 of 2 dx. I'm going to show you two ways to do this. The way I do this personally is I visualize it. I visualize it and I say, okay, well, let's think about 2 for a second. If I had an integral of 2, this is 2, right? I drew 2, right? This is 2 right here. And I do it from -1 to 9. Well, I have a rectangle, don't I? From -1 to 9. And the width of that rectangle is just 10, and the height is 2, so this must be 20, right? So it just that to me is the easiest way to do it, of a constant. So, oh, that's clearly 20. This is the width. This distance is the width. That's the height. So that must be 20. But I'll also show you how to do it. I'll show you how to do it a different way, in case that doesn't make sense for you. So that's 27.5. That's the answer here. Again, but before I go on, I will show you this. So you could also do fundamental theorem of calculus here. The integral, the antiderivative of 2 is 2x from -1 to 9. Plug in the 9. So we get 2 times 9 is 18 minus 2 times -1 is -2, which equals 20. So I could also do fundamental theorem of calculus, or you can do it visually, like, you know, with kind of geometry. Either way works. Whatever works for you. This works for me, but this might work better for you. We're getting there. The graph of g prime, the first derivative of g, consists of a semicircle of radius 2 and 2 line segments as shown in figure above. If g of 0 is 1, what is g of 3? So this is like and same thing of initial value. Like you see this setup, you're like, ah, this is initial value. I'm going to need that setup, right? I'm going to need sp plus integral stet of some like derivative dx, right? So this is the scaffold, right? Well, my starting point is 1. And then I'm going to take the integral from 0 to 3 of g prime of x dx. Okay, that's my scaffold, that's my version of it. Okay, so the 1 is easy, but now I need to get the area from 0 to 3. I think it's always helpful to kind of shade what you're looking for, just like, so it's never a question. This is what I want. So let's do the triangle first. Triangle's easy. It's a 1 by 2. 1 by 2. 1 times 2. 1 times 2 divided by 2 is 1. This is 1 right here. Right. Area of a triangle. 2 times 1 divided by 2. This is a circle, right? You can imagine this is one big circle. You need to know this for the test, right? The area of a circle is what? Pi r squared. That's right. Pi r squared. So if I have a quarter of a circle, the area of that would be pi r squared over 4. Right? Similarly, if I had a half circle, if I was going the other way, I had a half circle like this, that would be pi r squared over 2, because it's half of that. But this is the one I want, pi r squared over 4. So let's do it. My r here is 2, radius is 2, so it's going to be pi 2 squared over 4. That's 4 pi over 4. That's pi. So this distance is 1 plus pi. So this is saying this integral, this all right here is 1 plus pi. 1 plus pi. So what I have is 1 plus 1 plus pi. That's 2 plus pi, which is pi plus poo. Same thing, different order. All right. Last page. Oh, we got a couple. We got 2 more to go. All right. These are some gimmies. These are some gimmies, guys. You see this on the test. There should be no hesitation here. This is just fundamental theorem of calculus, and so you have to know fundamental theorem of calculus. First, you take the antiderivative of this, which is going to be 8x to the 4th over 4 minus 3x to the 3rd over 3. I'm going to simplify that. 8 over 4 is 2x to the 4th minus 3 over 3 cancels. Right, this cancel. Which is minus x to the 3rd, all from -2 to 1. And then we'll do the order right, so it's going to be just f of 1 minus f of -2 here. So plug in the 1, you're going to get 2 times, I'll show you the full work, 2 times 1 to the 4th minus 1 to the 3rd minus 2 times -2 to the 4th minus -2 to the 3rd. Actually, you guys might struggle with this. The setup is easy. I think from what I saw in class, you guys kind of struggle with this kind of thing. 1 to the 4th is just 1, 1 to the 3rd is just 1. This is 2 minus 1, so just 1. Okay, because 1 to any power is just 1. Right, so that's just 1. 2 minus 1 is 1. Here, -2 to the 4th is, well, 4, 8, 16. 16 times 2 is 32. So this is saying 32 right here. 32 minus -2 to the 3rd is -8. So it's minus a -8. So this is a 40. So it's 1 minus 40. 1 minus 40 is -39. So this is the answer here. I'm sure that there's like some other, like, I'm sure some of these are like kind of common mistake answers, but you know if you got it right or not if like you see your answer here. That's why multiple choice is kind of nice. All right, next one. Similar kind of problem. It's from the delta 3.4. You have to simplify this before you take the integral, so you have to do the box, you know, or however you do it. Maybe you box it, maybe you FOIL it. I don't really care what you do, whatever works for you. X cubed plus 1, x plus 1, right? And you would multiply them. And when you do that, I'll just go ahead and get it. It's x to the 6th plus 2x to the 3rd plus 1. It should be a plus. Okay, so when you take the integral of that, or you know, you integrate that, you're going to get x to the 7th over 7 plus 2x to the 4th over 4 plus x plus c. Because it's remember, it's an indefinite interval right here. And then that's just 1/2. So this is really just x to the 7th over 7 plus 1/2 x to the 4th plus x plus c. And I see that answer right here. B. Okay. 14. A particle moves along a straight line for 6 seconds so that its velocity in centimeters per second is modeled by the graph shown. During the time 0 to 6, what is the total distance the particle travels? Total distance, so you should be familiar with this total distance. Total distance in your head, you should be thinking, okay, that's integral a to b of the absolute value of v of t dt. What does this mean in this context? Because, you know, you're not using your calculator, you're not doing abs, you know, you're not doing math num abs. You're doing a graph. And so what it really means is that the negative areas count as positive areas. That's all this means. So we're going to find the integral from 0 to 6, but we're just going to make all the negatives positive. Okay, so here, let's like separate this out. This is going to be 4. Right here, this is a 2 by 1. So this is, that's worth 1. Right here, this is a 1/2. It's technically a -1/2, but like I said, we count it as positive now. So now we add them all up. That's 6.5. D. Okay, questions on that? I mean, you can't ask me questions, but I think that's pretty straightforward. The point here is that it says total distance. If it said displacement, right, displacement would be 5 minus 1 minus a half. So the displacement would be 3.5. The distance is 6.5 because it's absolute value. See the difference? And so you can see they would try to maybe get you with that 3.5 there. But the answer is 6.5 because it's total distance. You got to read it carefully. All right, 15. The number of bacteria in a container increases at a rate R of t. There are 1,000 at the beginning. Which of the following expressions gives a number of bacteria at time t equals 3? So, this is like, this is kind of like one of the deltas. 3.5, I think, is like this one. And you're not asked to actually solve anything. You're just like doing the setup. So this is like this is the same thing as we're doing before. This is the initial value 1, right? If I want the number at a future time, right? Let me write this out. Number at a future time, I'm going to write the full expression. So I need to have my starting value 1,000 plus the integral from 0 to my end 3 of my rate dt. So I mean, it's absolutely d. But let me like pause here for a second because this question could have been different just depending on like what it was asking. If it said the displacement or the change in the number of bacteria between 0 and 3, this is the change in the number right here. So that's this whole thing gives you bacteria at t equals 3, where this one right here is the change in bacteria from t equals 0 to t equals 3. So I just want to make sure that's clear. Like, this is giving like the displacement, and this is the end result, the end number of bacteria. Okay, nearly there. 16. On a certain day, the total number of pieces of candy produced in factory since open is multiplied by C. Okay, this is important. So I guess when you're reading it, look at total number. Okay, this is multiplied by C. Okay, a differential function on the number of hours since the factory opened. Additional function of the number of hours since the factory opened. Which is the following best interpretation of C prime of 3 equals 500? Okay. So it's giving me, this C is giving me the total at a specific point. This is like analogous to S of x, to the position. Essentially like this, you're looking at the position and you're taking the derivative. So think about like, the position is giving you like length at a specific time. This is giving you, what are we even measuring here? Candy at a specific time. So when we take its derivative, we're going to get candy over time. So we're getting a rate. So let's look at the options. The factory produces 500 calories. No, it's not telling me how much it's producing, right? It produces 500 pieces in the first 3 hours. No, it's not giving me a quantity. It's going to be a rate. I'm looking for a rate. The factory is producing candy at a rate of 500 pieces per hour. 3 hours after it opens. Yes, that sounds pretty good. I'm gonna like mark that one because that one sounds like it to me. The rate at which the factory is producing candy is increasing at a rate of 500 per hour 3 hours after it opens. Oh well, no, this is not correct. So here's some key things that I know is true. C is measured in like the quantity of pieces. So C prime must be pieces per hour. So see how this says pieces per hour? That's key. See, this one down here might be confusing to you because it's like, oh, this is rate, but see this one, pieces per hour, that indicates the second derivative. That would be that, right? The rate is increasing at a rate. The rate of a rate is the second derivative. That's that one. This one is this first derivative. Okay, and then these would be like, no. This is just straight C of 3. A is just straight C of 3, and then B would be an integral. Yeah, A would be like C of 3, and then B would be the integral from 0 to 3 of C prime of t dt. So this is C is just straight C prime of 3. Last one of this section. Yep. So this is a Riemann sum to integral notation problem. You remember these from the delta. I think they're in 3.1. Essentially, the way they work is it's a minus b over n is the width. Sorry, b minus a over n is the width. So you're looking for that. That's this right here. And then you have f of a plus b minus a over n. Usually it's k. That's kind of, those are the elements of the sigma notation, and then you have like the k equals 1 to n, and this should be like limit as n goes to infinity. So it's missing the n goes to infinity one, but that's okay because it's just saying right Riemann. It's not saying infinite. So you're looking to match this to one of these, and so the first thing you want to do is check b minus a over n. That's easy. So you're going to do this minus this needs to match this. So let's check those first. So 7 minus 2 is 5. 7 minus 2 is, these are all equal 5. So that doesn't really help us because they're all 5 over n. Because the difference between all of these is 5. So that doesn't really help us here. Here, so it's ln. All right, well, they all have ln. That doesn't help me very much either. 2 plus 5 over nk. So if we look at this right here, so this a, that's like, if you look at the integral, it's a to b. This is the a that's going up, this bottom one. So if I look, I'm going to take b as an example. If I were to write the Riemann sum of b, I would need to put in for x right here, this would be 2 plus 5 over nk. But there's already a 2 here. This cannot be it because this would get me 4. Okay, because I started at 2, this x right here would become like 2 plus 5 over nk. Let me write that in so it's clear. Right, so that would make that a 4. So it cannot be that one. And right, I have 2 here. So if you look at this one, ln 2 plus 0 plus 5 over, but this is going to have a 5 out in front. So because of this 5 out in front, that's going to completely change this. That would actually make that a 25. So in this one, this would come out as like it would come out as a 10 plus 25 over nk. That would be that one. So that's not right either, because you would have to multiply that entire expression by 5. That's not going to work. This one is going to have the same issue. You're going to multiply that whole thing by 5. This is the same problem here. So that one's out, that one's out. It has to be this one. And I'll prove to you why this one works. So let me just do it from scratch. Integral 2 to 7 ln x dx equals, so as a summation, it's going to be k equals 1 to n. It's 7 minus 2 over n, so it's 5 over n. And then you just rewrite the function as it is, ln, and then you replace the x with that starting point 2 plus that same width, 5 over n k. Boom. That's it. And look, that matches that exactly. I wrote it in a different order, but it's exactly right. So be familiar with 17. Okay, FRQ time. So this FRQ, I want to say this one was taken, I think this one is the 2013 one. I should have made a note of that, but I think this is the 2013 FRQ, which is really funny because this was the year I took the test. And it just happened to fit it well, so that's why I chose this one. But you're going to get an FRQ. Here, you're going to get 2 FRQs. This is the, we'll talk about this in class, but these are called linear motion problems. You're going to get one of these. It's going to be set up just like this. There'll be a problem. There'll be like A, B, C, D. It will not be the same questions as these. It'll be different questions, right? This is an example. If you want more examples, you can find more examples of these online. You search like linear motion If you go to Calcmetic, there's a website called Calcmetic, and you look at their FRQ types. If you go through that, let me write that clearer. Calcmetic FRQ types, and you'll see linear motion. I'll put this all in the email, so maybe just ignore this. That will get you more examples of these kinds of questions. If you're looking for more practice, you can get more practice there. Here we go. A particle moves, oh, by the way, this is calculator allowed, so you need a calculator for this one. Particle moves along a straight line for 0 to t. The velocity, from 0 to 5, the velocity of the particle is given by -2 plus t squared plus 3t all to the power of 6/5 minus t cubed. And the position of the particle given by s of t is known that s of 0 is 10. Okay, so some of this should look familiar to you, right? Okay, this is kind of a hint that you're going to have to be doing some starting, ending kind of thing going on. And even if you had no clue what to do, we're going to read through these in a second, you know you're going to have to put this into the calculator. It's a calculator problem. You have a guess that this is probably going to go into y1, right? So let's go ahead and do that. Let's start by just putting it into y1. If when in doubt, put it into y1. All right, you're in the calculator portion. Go ahead, put that in. All right, so it's going to be -2 plus x squared plus 3x parentheses. So just make sure you copy it exactly as it looks, and then to the power of. This is important, guys. When you do exponents, it's a fractional exponents. See this right here? Not correct. It's not that's correct. You have to put a parentheses around it. And this is actually on the newer calculators, you don't have to worry about that as much, but on this one you do. Math 3 different cubed. Yeah, this looks good to me, and we're going to set the window from 0 to 5. And this is going to kind of get us started here. And I can kind of look at it. So, okay, I got this velocity. All right, okay. So let's look at A. So A is saying, I want to find all the values of t from 2 to 4, where the speed is 2. Okay. So I made a mistake already. The window now should be 2 to 4 because it's asking for 2 to 4. So I got to change the window to match that. That's important, guys. So we should match the window to that. And speed. So when you think speed, you need to say this on the paper, by the way. You say, okay, well, speed equals the absolute value of v of t. Boom. Points just for doing that. Points just for doing that. Okay, you can actually see I gave you the keys to these on the back, which I'll be referring to throughout this, is that considering the speed needs to equal 2 is one of the points. So not only that, but we need to say we want that to equal 2. And then find it. So right now I have velocity typed in there. I need to change that to speed, and recall that speed is the absolute value. So what do you think you do? Well, you got to change that. You can do second delete to insert, and I'm going to go to math, num, abs, and I'm just going to change the absolute value. Once we recalculate, it'll look a little nicer. And now we're going to graph it, and you'll see this should be coming out all positive. Right, so I want to find everywhere that is equal to 2. My window looks a little, well, it's actually fine. My y-max is 4. So I'm going to set another one called 2, because we need to find out where it equals 2. There we go. There we go. Second trace to get to calc. And then we're going to go down to intersect. And then I'm going to move this over, and you move it close to where you think it intersects. You go enter, enter, enter. And that's the intersection 3.128. Okay, so t, important. T equals 3.128. That's the all values t. So make sure that t is matching this t here, right? And then we'll do it again. Second calc, intersect, and we'll move it over to the other end, the other intersection. Enter, enter, enter. And that's 3.473. Okay. T equals 3.473. And that. Okay. So you can say, you know, the speed of the particle is 2 at t equals 3.128 and t equals 3.473. Alright, write an expression involving an integral that gives position of s of t. Use this expression to find the position of the particle at t equals 5. This is what we've been doing. So it's the starting position is 10. Starting position is 10. And I'm going to add the integral from 0 to some t of v of x dx. Okay. You might be wondering, like, okay, why is that t, that's x now? Again, like the t and the x are kind of like arbitrary. The x is there so it doesn't match the t, if that makes sense. And because it asked me to find the position in terms of t, so this is s of t, that means that I need to plug a t in there. To an extent, it didn't really matter what letter I put in there for x, it just couldn't match the t. That's why it's there, because you don't want to put in, you're not putting that t in for both of these at the same time. You're just like, you're putting it in here and then you're finding the integral of that. I know it's kind of confusing, but if you're writing your integral in terms of t, this also has to be a t. I assume that they would have also accepted s of x equals 10 plus integral 0 to x f of t dt. I assume that, but maybe not. So this maybe is how you would think to write it, but because it's asking you to write it in terms of s of t, right? This is s of t here. That's why it's written the way it is. So I'm going to go with what the key says, and we're going to go this as a solution. Here we go. So then use it to find the particle at t equals 5. Well then, at t equals 5, s of 5 would be 10 plus the integral from 0 to 5 of v of x dx. And that's in the calculator. So back to here. We're going to go back to y equals, and I'm actually going to get rid of that absolute value because I don't want the distance, I want displacement. So I'm going to get rid of that absolute value. And then I'm going to go back to home, and then I'm going to do math 9, and I'm doing the integral right now. But instead of having to, I mean, I could copy that all in again, and if you wanted to, you could, but I don't want to do that. I'm going to go to vars, y vars, function y1. What that's doing is it's copying that whole function that I wrote before. It's just putting it in there, so I don't have to retype it again. So it's really helpful when you want to do things multiple times. Comma x, comma 0, comma 5, close it. It's, let's see what it is. Taking its sweet time. Negative 19.207. We're going to add the 10. So this together is negative 9.207. So s of 5 equals negative 9.207. And that's it. Okay. So I think a common mistake that students could make here is that they could do the copy and paste thing, but they would forget to take off the absolute value. Remember, because it's v of x or v of t, it's not the absolute value anymore. Find all the times from 0 to 5 when the particle changes direction. So back to the graph, and I can actually get rid of, I'm going to do a couple things here. So I'm going to get rid of, I'm going to change the window back to 0 to 5 because that's what it wants, 0 to 5. Make sure you always match the window to that. It's important. And then I'm going to go back to y equals, I'm going to get rid of the 2. I don't need the 2 anymore, so we can clear that. Now let's graph it. So when it changes directions, again, you just need to know this. This is for the table. Changes directions happen when it equals 0, right? So I'm looking for where v of t equals 0 and changes signs. That's when it changes directions. So on here, where does that happen? Well, I can see where it's happening visually there and there, and now I gotta find it. Second calc 0, and then I'm going to move my cursor over here to the left. There it is, taking its sweet time. Here it goes, left bound on the left side, right bound on the right side, and then one in the middle, and that would be 0.536. So t, one of my values is t equals 0.536, and my other value is 0 on the far right. It's going to take a little bit to get over there. Okay, moving over, there we go. Okay, then it's on the left here, and then it's on the right, one below it, then one in the middle, enter. It's 3.318. 3.318. So it says justify your answer. I found the answers, and I mentioned that it should equal 0, but I haven't justified yet, and it's really important to justify your answer. So I'm going to say v of t changes signs from negative to positive at t equals 0.536. Again, visual, negative to positive. And v of t changes signs from positive to negative at t equals 3.318. Therefore, the particle changes directions at t equals 0.536 and t equals 3.318. Does it have to be written exactly like this? No, it does not. As long as you're communicating to me that it's changing signs at the point, equaling 0 and changing signs at these points, and that's why it changes directions, right? So make sure you're saying that. Is the speed of the particle increasing or decreasing at t equals 4? Give a reason for your answer. So you need to know when this is true. So remember, particle is increasing speed if v of t and a of t are the same, and it's decreasing if they're different. So we need to find v of 4, and then we need to find a of 4. So let's do that. So v of 4, I'm going to show you some more tricks on the calculator. V of 4 you're going to get by going to vars, y vars function, y1. So if you just do that and put a 4 after it, like that, you're gonna get y of the velocity of 4. Because remember, that's like my velocity function right there that I put in y1. That's this right here. But I'm calling it, and then I'm saying, and that parentheses after is like putting a 4 into it. So okay, so it's a negative 11.476. Negative 11.476, and then a of 4, it means I need to take the derivative. To get from velocity to acceleration, you gotta take the derivative. So we do math 8, and again, instead of copying and pasting it, instead of typing, I'm gonna copy and paste it. Vars, y vars function y1, comma x, comma 4, enter. Negative 22.296. So this is less than 0, and this is less than 0. Because velocity and acceleration have the same sign, negative, right, parentheses, the speed is increasing. All right, that's FRQ number 1. All right, last one here, FRQ. So like I said, in the test, you're gonna get multiple choice of both types, calculator, non-calculator, and get an FRQ of both types. It'll be this kind of FRQ. Like, it'll be a linear motion one. This one is a graph one. Again, same thing, Calcomedic has more examples. I think these are just called like graph analysis, I think they're called. I'll put that in the email. So the graph of the function f consisting of 3 line segments and a quarter circle above, let g be the function g of x equals from 1 to x f of t dt from the average rate of change from -5 to 5. Okay. So I think like when you're reading these problems, like my advice is to really relax, to slow down, to read the question carefully, and like, you know, don't panic. You can do this. I'm not giving you anything you can't do. You can do everything I give you. You have the knowledge, just read it carefully, okay? All right, this isn't really that helpful. Quarter circle, that is helpful because now I know that that's a circle. That'll probably be relevant later. And you know, g of x is an area function. So even before I begin, I know that, you know, the derivative of g of x is f of x. That's probably going to be relevant, which is going to come up here. And then it says find the average rate of change of g from x equals -5 to 5. Well, average rate of change, you guys remember this? Average rate of change? It's f of b minus f of a all over b minus a. You can do that. You've done that before. You can do all this. So that's saying g of 5 minus g of -5 all over 5 minus -5. Okay, well, 5 minus -5, well, that's just 10. That's easy. G of 5, what's g of 5? Well, I'm going to plug in a 5 into this. I need the area of f of t from 1 to 5. So I'm going to go up here. We're going to get that from 1, 2, 3, 4. So I need this area right here. So this is, what is it? It's a triangle and a rectangle. 1, 2, 3, 4, 5. You can even count the squares. That's an 8. And this one right here is a 2 by 4. So it's a 4 because 2 times 4 is 8 divided by 2 is 4. So that's just 12. And g of 5 is just 12. That's a 12 right here. Okay. Then g of -5, the area from 1 to -5. So a little more challenging. I want this from here to 1, 2, 3, 4. I need basically all this. I just need to go backwards. So you find this area. So first, I'm going to find the area from -5 to 1 of f of t dt. That's gonna, and then I'll flip it when I'm done. So the area of this is 3 by 1, 2, 3, 4. So this is 12. This is -6, right? I'll come back to that in a second. This is 1 by 2. This is a -1 because it's 1 times 2 divided by 2 is -1. And this is a circle. This is what I talked about before. The area of a circle is pi r squared. And it's a quarter, so it's pi r squared over 4, right? So this is pi r squared over 4. And my r is 2, so this is just 4 pi over 4. And so this is a -pi. So altogether I get, this is -7 minus pi. But I don't want -5 to 1, I want 1 to -5. So I'm going to flip it. So the integral from 1 to -5 is the negative of these two, -7 minus pi, which is going to be 7 plus pi. Okay, so whatever you get, at the end you just make it negative. And that's going to give you the original. So you got 12 minus 7 minus pi, because I got to subtract both of these. So that comes out to 5 minus pi over 10. And that's the answer to A. Okay. B. Find the instantaneous rate of change of g with respect to x at x equals 3, or state that it does not exist. So instantaneous rate of change, you need to know, okay, that's derivative. So g prime of x is equal to f of x. I said that before. So that means I just need to find f of 3. Okay, f of 3. This is section 3.3. I think this one's from 1, 2, 3, up 3, 1, 2, 3, 4. So it's 4. It's 4. Okay, that's it. The instantaneous rate of change of g at x equals 3 is 4. It says a sentence. I mean, you want to go ahead and write a sentence, even though I understand what this means. Write the sentence. The instantaneous rate of change of g at x equals 3 is 4. Two more. On what intervals, if any, is g concave up? Justify your answer. So it's concave up when you can think of this different ways. The way I think about it is like when the first derivative, which is f of x, is increasing. That's when it's concave up. So you're just going to go back up here. Where is f of x, the curve increasing? Well, it's increasing from -5 to -2. Let's go ahead and write that. So we're going to have -5 to -2. And we're going to have also increasing here from 0 to 3. So -5, -2, and 0 to 3. So my sentence is going to be, I'm just assuming that's like as a note to myself. So I would say over here, G is concave up on the intervals. Technically these would be bracketed, but the AP test doesn't take off points for brackets like that, whether or not you, whichever one you write, technically it would be these. And 0, 3, because is increasing. Essentially you're saying because the derivative is increasing, right? That's what I was saying here. It's concave up when that's increasing. So that's what I'm saying here. I'm just saying it in words. Last one. Put all the x values in which g has a critical point, classify each critical point as a local min, local max, or neither. Justify your answer. So critical points happen, this is in the notes, when the derivative equals 0, which is just saying where does f of x equal 0? Okay, well, where does that happen? That happens at happens at -2, and it happens at 1. Okay, so so I'm going to just write it as a note for right now. X equals -2 and x equals 1. So we would say, I could say like this happens at these points. And then over here, I'm going to say G has critical points at x equals -2 and x equals 1 because g prime of x, f of x equals 0. Then let's look at them. So what do we have here? So at this point, we do not have any kind of relative min or max because it doesn't change signs, it doesn't cross over. But here we do. We're going to have a relative min because we're going from negative to positive. So right there, that's a relative minimum, and this is neither. So we could say multiple different ways. You can say in different ways. So like a simple way to say it is G has no local min max at x equals -2 because G prime does not change sign. And then here you can say G has a local min at x equals 1 because G prime changes from negative to positive. Obviously, you would write that in better space. I kind of crammed that in there. But all these answers, guys, are on the answer key at the back. So if you're curious, like, I was essentially just copying these answer keys, what they were writing. So, I mean, I would accept this in different words, right? But you have to be clear. And it says justify your answers. You have to say why. It's not enough to write this. It's absolutely not enough. It's not enough to point to this and be like, oh, this is neither, and this is a min. That's not enough. You can't do that. You have to write the sentences out. You have to say to me why. And that's why in the last test, like at the very end, I had you justify all those times, because you need to get used to that. You have to justify the why. All right, that's the practice test. Well done getting this far.